Hi and welcome back at the IPv4 addressing part 3. At the first part of the IPv4 addressing, we described the structure of an IPv4 address, including the network portion, the host portion, and the subnet mask. We also compared the characteristics and uses of the unicast, broadcast, and multicast IPv4 addresses, and we even explained the public, private, and reserved IPv4 addresses. And at the second part, we explain how subnetting segments a network to enable better communication. We calculated IPv4 subnet for a /24 prefix, and we even calculated IPv4 subnet for a /16 and /8 prefix. And now, in the third part, we will, given a set of requirements for subnetting, implement an IPv4 addressing scheme, and we will explain how to create a flexible addressing scheme using variable length subnet masking, and we even will implement a variable length subnet masking addressing scheme. So let's continue. The organization network may use both public and private IPv4 addresses, and this will affect how you will subnet your network. Here in the figure, it is shown a typical enterprise network. We have the intranet, where there is internal part of the company's network accessible only within the organization. Devices in the intranet use private IPv4 address. We have even the demilitarized zone. This is a part of the company network containing resources available to the internet, such as web server, and devices here use the public IPv4 addresses. Both intranet and demilitarized zone have their own subnetting requirements and challenges. The intranet uses private IPv4 addressing space. This allows an organization to use any of the private IPv4 network addresses, including the 10.0.0.0/8 prefix with 24 host bits and over 16 million hosts. Using the network address with a 24 host bits makes subnetting easier and more flexible. This includes subnetting on an octet boundary using /16 or /24 prefix. For example, the private IPv4 network address 10.0.0.0/8 can be subnetting using a /16 mask. And as it is shown in this table, this will give us the result of 256 possible subnets and will give us the possibility of around 65,000 hosts per subnet. If an organization has a need for fewer than 200 subnets, allowing for some growing, this gives each subnet more than enough host addresses. Another option using the 10.0.0/8 private IPv4 network address is to subnetting using a /24 subnet mask. And as it is shown in this table, it gives us the result of around 65,000 possible subnets with 254 possible hosts per subnet. And here it is explained the range of the IP addresses for the host and the broadcast in each table. The 10.0.0/8 can be subnetted using any other number of prefix lengths such as /12, 18, 20, or more. This would give us the network administrator a wide variety of options. Using a 10.0.0/8 private IPv4 network address makes subnet planning and implementation easy. And what about the demilitarized zone? What can you say about that? Because these devices need to be publicly accessible from the internet, the devices in the demilitarized zone require public IPv4 addresses. The depletion of public IPv4 address space became an issue beginning in the mid-1990s. And since 2011, and we are running out of the IPv4 address space. Although organizations are making the transition to IPv6, the remaining IPv4 address space remains severely limited. This means that an organization must maximize its own limited number of public IPv4 addresses. This requires the network administrator to subnet their public address space into subnets with different subnet masks in order to minimize the number of unused host address per subnet. And this is known as variable subnet length mask. To minimize the number of unused host IPv4 address and maximize the number of available subnets, there are two considerations when planning subnets: the number of host addresses required for each network and the number of individual subnets needed. The table here displays the specific of subnetting a /24 network. You will see there that is an inverse relationship between the number of subnets and the number of hosts for each subnet. The more bits that you borrow to create subnet, the fewer host bits remain available. If more host addresses are needed, the more host bits are required, resulting in fewer subnets. The number of host addresses required in the largest subnet will determine how many bits may be left in the host portion. You have to recall that of the addresses can be used, so the usable number of addresses can be calculated as the base exponential by the number of the bits that are borrowed minus 2 addresses that have been reserved for IP address of the network and the IP address of the broadcast for that network. The network administrator must devise the network address scheme to accommodate the maximum number of hosts for each network and the number of subnets. The address scheme should allow for growth in both the number of host addresses for subnet and the total number of subnets. To understand the efficiency of IPv4 subnetting, let's take and consider an example. We have a corporate headquarters that has been allocated a public network addresses of 172.16.0.0/22 with 10 host bits by its internet service provider. And as it is shown here, it will give us around 1022 hosts for subnet. The corporate headquarters has a demilitated zone and 4 branch offices, each needing its own public IPv4 address. Corporate headquarters need to make best use of its limited IPv4 address space. And here in the figure, it is given the topology of consisting at 5 sites, a corporate office and 4 corporate office and 4 branch sites. Each site requires internet connectivity and therefore 5 internet connections. This means that the organization requires 10 subnets from the company's 172.16.0.0/22 public address. The largest subnet requires 40 addresses. And the 172.16.0.0/22 network addresses has 10 host bits as it is. The 172.16.0.0/22 network address has 10 host bits as it is shown in the figure. And because the largest subnet requires 40 hosts, we need a minimum of 6 host bits needed to provide addressing for 40 hosts. And this is determined by the formula of number 2, which is the base, exponential by 6 bits that are borrowed minus 2 addresses that are reserved for the network address and the broadcast address, equal to 62 hosts. And this is the subnetting scheme, and as you can see, we will be able to create 16 subnets since we are borrowing 4 bits, and we can calculate the number of subnets that will be created by base number 2 exponential by 4 bits that are borrowing to create the subnets as a result of 16 subnets. And with this, now we are expanding even our subnet mask from /22 to /26. And now these are the subnet assignments to each site and the internet service provider connectivity. Because of the depletion of public IPv4 address space, making the most out of the available host address is a primary concern when subnetting IPv4 networks. Using traditional subnetting, the same number of addresses is allocated for each subnet. If all the subnets have the same requirements for the number of hosts, or if concerning IPv4 address space is not an issue, these fixed size address blocks would be efficient. But typically, with public IPv4 address, this is not the case. For example, let's have this topology as it is shown in the figure that require 7 subnets, 1 for each of the 4 LANs and 1 for each of the 3 connections between the routers. Using traditional subnetting with the given address of 192.168.20.0/24, 3 bits can be borrowed from the host portion in the last octet to meet the subnet requirement of 7 subnets, as it is shown here in the figure. By borrowing 3 bits, we will be able to create 8 subnets and leave 5 host bits within 30 usable hosts per subnet. This can create the needed subnets and meet the host requirement of the largest LAN. But these 7 subnets could be assigned to the LAN and WAN network as it is shown here. Although this traditional subnet meets the need of the largest LAN and divides the address space into an adequate number of subnets, it results in significant waste of unused addresses. For example, only 2 addresses are needed in each subnet from 3 ones, as you can see here. Because each subnet has 30 usable addresses, there are 28 unused addresses in each of these 3 subnets. And as it is shown in this figure, there is a result in 84 unused addresses. Because we have 28 for each, 28 times 3 give us the 84 addresses are unused. Further, this limits future growth by reducing the total number of subnets available. This inefficient use of addresses is characteristic of traditional subnetting. Applying a traditional subnetting scheme to this scenario is not very efficient and is wasteful. That's why the variable length subnet mask was developed to avoid wasting addresses by enabling us to subnet a subnet. And as we saw in all of the previous subnetting examples, the same subnet mask was applied for all the subnets. This means that each subnet has the same number of available host addresses. As it is illustrated in the left of this figure, traditional subnetting creates subnets of equal size. Each subnet in a traditional scheme uses the same subnet mask. As is shown in the right side of the figure, the variable length subnet mask allows a network space to be divided into unequal parts. With the variable length subnet mask, the subnet mask will vary depending on how many bits have been borrowed for a particular subnet. Thus, the variable stands at the part of variable length subnet mask. And variable length subnet mask is just subnetting a subnet. The same topology that we used previously is shown here. Again, we will see that we are using the 192.168.20.0/24 network, and the subnet is for 7 subnets, one for each of the 4 LAN and one for each of the 3 connections between the routers. The figure shows how the network 192.168.20.0/24 it is subnetted into 8 equal sized subnets with 30 usable host address per subnet. 4 subnets are used for the LANs and 3 subnets could be used for the connection between the routers. However, this connection between the routers requires only 2 host addresses per subnet, 1 host address for each router interface. Currently, all subnets have 30 unusable host addresses per subnet. To avoid wasting 28 addresses per subnet, variable length subnet mask can be used to create smaller subnets for the inter-router connection. To create smaller subnets, we use one of the subnets that we will divide it. And here in the example, we are dividing the last subnet, the 192.168.20.224/27, which will be further subnetted. And here it is shown the last subnet that has been subnetted further by using the subnet mask of /30. And you want to say why 30? We have to recall that when the number of needed host address is known by the formula A2 exponential by the number of the host bit remaining minus 2, this will provide us 2 usable addresses. 2 host bits must be left in the host portion. Because there are 5 host bits in the subnetted 192.168.20.124/27 address space, 3 more bits can be borrowed, leaving 2 bits in the host portion. The calculation of this point are exactly the same as those used for traditional subnetting. The bits are borrowed and the subnet range are determined. Here in the figure, it is shown how from the 427 subnet has been assigned to the LAN and 3 of the /30 has been assigned for the inter-router links. This variable length subnet mask subnetting scheme reduces the number of addresses per subnet to a size appropriate for the network that requires fewer subnets. Subnetting subnet 7 for inter-router links allows subnet 4, 5, and 6 to be available for future network, as well as 5 additional subnets available for inter-router connection. By using the variable length subnet mask subnets, the LAN and the inter-router network can be addressed without unnecessary waste. At the first figure, it is shown the network address assigned and the IPv4 address assigned to each router interface. Using a common addressing scheme, the first 5 IPv4 address for each subnet is assigned to the LAN interface of the router. Host and each subnet will have a host IPv4 address from the range of host addresses for that subnet and an appropriate mask. Host will use the address of the attached router interface as the default gateway address. Here in this table, it is shown the network address and the range of host addresses for each network. The default gateway address is displayed for the 4 LAN networks. You have to remember that before you start subnetting, you should develop an IPv4 addressing scheme for your entire network. You will need to know how many subnets you need, how many hosts a particular subnet requires, and what devices are part of the subnet, which part of your network use private address and which use public, and many other determining factors. A good addressing scheme allows for the growth. A good addressing scheme is the sign of a good network administrator. Planning IPv4 network subnets requires you to examine both the need of an organization network usage and how the subnets will be structured. Performing a network requirement study is the starting point. This means looking at the entire network, both the intranet and the demilitated zone, and determining how each area will be segmented. The address plan includes determining where address conservation is needed and where there is more flexibility. Where address conservation is required, the plan should determine how many subnets are needed and how many hosts per subnet. As we discussed, this is usually required for public IPv4 address space within the demilitated zone. This will most likely include using the variable length subnet mask. Within the corporate internet, address conservation is usually less of an issue. This is largely due to using private IPv4 addressing, including 10.0.0.0/8 with over 60 million host IPv4 addresses. For most organizations, private IPv4 addresses allow for more than enough internal addresses. For many larger organizations and internet service providers, even private IPv4 address space is not large enough to accommodate the internal needs. This is another reason why organizations are transitioning to the IPv6 network. For intranet that use private IPv4 address and the demilitated zones that use public IPv4 address planning and assignment is very important. Where required, the address plan includes determining the needs of each subnet in terms of size. You may know that how many hosts there will be per subnet. The address plan also needs to include how host address will be assigned, which host will require static IPv4 address, and which host can use a dynamic host control protocol for obtaining their addressing information. This will also help prevent the duplication of addresses while allowing for monitoring and managing of addresses for performance and security reasons. By knowing your IPv4 address requirement, you will be able to determine the range or ranges of host addresses that you implement and help ensure that there are enough addresses to cover your network needs. By the other side, within a network, there are different types of devices that require addresses. We have the end user clients. Most networks allocate the IPv4 address to client device dynamically by using the DHCP server. This reduces the burden of network support staff and virtually eliminates entry errors. With the DHCP, addresses are only leased for a period of time and can be reused when the lease expires. This is an important feature for networks that support transient user and wireless devices. Changing the subnetting scheme means that even the DHCP server needs to be reconfigured and the clients must renew their IPv4 address. We have even the servers and peripherals. This should have a predictable static IPv4 address and use a consistent numbering system for these devices. We have even servers that are accessible from the internet, and these servers we need to be publicly available on the internet and must have a public IPv4 address, most often accessed using the network address translation. In some organizations, internal servers, not publicly available, must be made available to the remote user. In most cases, these servers are assigned private address internally, and the user is required to create a virtual private network connection to access that server. This has the same effect as if the user is accessing the server from a host within the intranet. We have the intermediary devices. These devices are assigned addresses for network management, monitoring, and security. Because you must know how to communicate with an intermediary device, they should have predictable, statically assigned addresses. We also have the gateway, that are routers and firewall devices that have an IP address assigned to each interface, which serve as the gateway for the hosts in that network. Typically, the router interface uses either the lowest or highest address in the network. When developing an IP addressing scheme, it is generally recommended that you have a set pattern on how addresses are allocated to each type of device. This benefits administrators when adding and removing devices when they are filtering traffic based on the IP, as well as simplifying the documentation. And with the third part of IPv4 addressing, we are adding all the information about the addressing at IPv4 networks. Thank you for being with me. And for those who are new at this channel, do not forget to subscribe and hit the notification button for the new videos that will be uploaded. Thank you again.